The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
Well, it's a pleasure to welcome Dr. Dan Hooper from Fermilab in Chicagoland area to the Into the Impossible podcast, which is a podcast as part of the Arthur C. Clarke Center for Human Imagination. And some exciting news, we were just recently picked up for distribution using the University of California TV network. So this video may appear eventually on a UC channel near you, which has a huge audience of basically millions of people. And it's, of course, available to the whole internet. So that covers a few dozen people, I'm sure. But it's a pleasure to welcome Dan. Dan has a new book called At the Edge of Time. He's on a book tour right now. Happens to find him in the same time zone as us, but not exactly the same state. And I thought we would begin with a little introduction to, who you are, what you do, how you spend your time, and the kind of work that you do exceptionally so in terms of bringing science and education to the public. So Dan, tell us about yourself. How'd you get here? What's your world line from childhood to today?
Well, it's a long and open-ended question, but so I'm a particle physicist turned astrophysicist. I never thought I'd be an astrophysicist, but that kind of happened by accident. I split my time between Fermilab and the University of Chicago, and I work on things like dark matter and cosmic rays, and neutrinos, and things like this. In terms of outreach and education, stuff like that, one of my favorite parts of my job is the teaching end. I really enjoy being in the classroom. I kind of take every opportunity I can to do that. This book, the new book, is my third book. So I've been doing this for a while, but I'm particularly excited about this one. I've spent more time with this one than I spent with the others. And I think maybe this is a good way to reach a wide audience about the sort of work that you and I do, and bringing the awe and wonder of the universe to many people as we can.
I'm curious how you got started in particle physics, and then it sounds like you kind of accidentally were led by your curiosity, imagination, things that we care about and we'll discuss. How'd you get interested in just physics and science, generally speaking, when you were a kid? What was that like? The path?
Well, it didn't happen when I was a kid. I know most of our colleagues, they have a story about, in kindergarten, they decided they wanted to be this specific subfield of scientists that they are now, and all these things. I have nothing like that. I grew up in the very rural Minnesota. Not only did I not think I wanted to be a scientist, I don't think I had any idea what it meant to be a scientist. I just had no encounters or experience with that. I took normal science classes in junior high and high school, but I didn't find them very exciting. Physics was rolling things down inclined planes. It wasn't, the cool stuff. And then I go to college, not for science. I intended to be a music student.
Wow.
And I got kind of disillusioned with that, tried a bunch of other things, and eventually wound up taking a modern physics class and falling in love with it. So in that one quarter, I learned about relativity, a little bit about it anyway. I learned a little bit about quantum mechanics. And these were the two most interesting things I'd ever heard about in my life. I knew that from the very beginning there. And I suddenly became a good student because I cared for the first time. And I worked hard and aggressively, and I just kept looking at these sorts of cool, counterintuitive science, physics things from as many angles as I could. Next thing you know, I'm in grad school trying to study particle physics. And like you said, I just kind of, my curiosity and imagination keep pulling me towards the cosmos. The next thing you know, I'm an astrophysicist and a cosmologist, along with a particle physicist.
And curious as to whether you completely disconnected your love of music. Do you still play music? I have friends in Chicago that are in, choruses and it's all sorts of orchestras, and there's no shortage of aesthetic activities for you in Chicagoland. So tell me, were you playing an instrument? Do you still play an instrument?
Sure. So, I play quite a few instruments, but the one that I really play is guitar. I taught myself to play when I was 15 or so, and got pretty good. Been in bands throughout my whole life. other than a couple of months here and there. For the last 10 years, I played in a soul band in Chicago called The Congregation. If you're ever in the Chicago area, then check us out. Or for that matter, just use the internet. There's that too.
Yeah.
So yeah, music's always been a big part of my life, but it's a very different part of my life than science. I go out of my way not to think scientifically about music. I don't want to know how it works or why it works. I want to feel it, not think it. And I enjoy using that other part of my brain.
Yeah, that's I always forget which brain side I use or not. I know it's only I aspire to someday use 10% of my brain, like they say people do. And not knowing much about music, the only instrument I play is the iPhone. But our mutual friend, Sean Carroll, is a big jazz aficionado. Our mutual friend Stefan Alexander is a professional jazz musician. And there is a Mark Kamiankowski, another theorist. I don't know what it is with theorists and jazz music or soul music, but seems to be
Is Mark a musician?
Mark is not a musician as far as I know, but he's a great aficionado of jazz.
Okay. All right.
And so there definitely seems to be something. I mean, dating back, look, Pythagoras, the great ancient Greeks and the Stoics, et cetera, loved they ruminate on the relationship between physics and music or math and music. I feel like a lot of times it's a little overblown, and like you said, sometimes you just want to listen to the music and not think about the music. So, but it's often been said. There's a book called Range. It's a new book where they do a study, of course, on people that have achieved great heights in all different endeavors, ranging from arts and science to politics, etc. And they look at, well, what were the hobbies of these men and women? What do they do? And they find the most successful, very strong correlation between success in a field, whether that's my least favorite thing, the Nobel Prize, or Pulitzer Prizes, or conductors in major symphonies, that they all have hobbies and they have enthusiasms that extend beyond that. And the social scientist who wrote this book, Range, I'm blanking on his name, might be Eisenstein, I forget. Anyway, he claims that using the kind of full connectome of your brain is what really the breadth of knowledge is what allows you to see new connections. So obviously you're not like thinking about that when you're writing down the new dark matter candidate or appraising a result from the experimental community, but it's certainly not lost on me how many people have these kinds of passions that at first glance seem orthogonal, but perhaps it had this interest for you, stimulated it.
Well, I think there's another important thing, at least in my experience, which is I have a very obsessive personality. When I get into something, I get really into something, which helps me to get good at it. So for the same reason that when I was teaching myself guitar, I would play for 6 or 8 hours a day most days, that later translated into me doing an awful lot of physics. And I think both things helped me to get good at that. That trait helped me get good at both of those things.
And then, so one thing that we look at in terms of the artistic connection between science and the greater human imagination is, of course, science fiction. We are affiliated and bear the name of Sir Arthur C. Clarke, who was obviously not only a first-rate science fiction author, but he contributed to a lot of innovative concepts in technology and in science. And for us, the kind of gateway drug for many of us was science fiction and introduction to great writers in the past. And your book, At the Edge of Time, now available from Princeton University Press, I believe, right? You have an impressive roster of people that have given you blurbs on the back of your book, ranging from Sean Carroll to my friend and yours, Katie Fries, and Whiteson, and of course myself. And what I said in this book, and I really believe, and I'm grateful I had a chance to read it, I said, where Stephen Weinberg's first 3 minutes left off, Hooper's At the Edge of Time picks up. A riveting tour of modern cosmology told by one of its savviest guides. Hooper's book takes us on a journey from our universe's formerly inscrutable past to mesmerizing possible scenarios in its far future. A fascinating story that is to be savored. And I kind of, I do see your book as kind of picking up where Weinberg's book left off, which is, obviously high praise, but I think it's, Weinberg's an outstanding writer and a communicator.
One of my favorites.
Yeah. And so I'm curious as to what were your influences? As I say, Weinberg, clearly is in this tradition that you're in. what were the influences that, in your life, and may not only be scientific, it might be science fiction or other. Can you tell us about, who are the mentors and people that you look to in the past?
So I'm a, eager reader. I read a ton, and most of it's nonfiction, but, quite a bit of fiction slips in there too. Some of my favorite books in my college years were popular physics books. Back then, I was a really big fan of Paul Davies, for example. He wrote a lot of books on these things, and John Gribben, people like Michio Kaku, and Leon Letterman. I read all these things back then. Hawking, Kip Thorne. And I think I read Weinberg a bit later. That was a little bit later. These days, there are a lot of our colleagues writing really good popular science. And I read a lot of this. A lot of our colleagues don't read popular science because they think they know all the science that's contained in it. And I read it, though, for how it's communicated, because I think we can become better communicators by seeing how it's done well. I enjoyed your book, for example. I enjoy, Sean Carroll you mentioned. I enjoy his writing a great deal. I just read some stuff from Jan 11 that I think is really first-rate, really exceptional work. I have Joe Dunkley's cosmology book on my shelf. I haven't quite read it yet, but it's right up there. It's on my very short to-do list. But then I really like reading nonfiction that isn't physics oriented, whether that be biology stuff or economics or other social science. History I find to be written in a really different format, so I don't know that I learn a lot about writing from that. But social science and not necessarily physical science, I really find helps my writing to get deep into that stuff.
Mm-hmm. So the aspect of your writing and the story, it's sort of journalistic, in that you're able to weave together a story that really does take us back, to before what was previously hidden, I think, in the writings. There really wasn't a book that filled in these gaps with enough technical, apologies to my vegan friends, but meat on the bone to satisfy. Like I often will read science. Popular science trade books, as they're called, because I can blow through them really quickly. Because I'm reading Sean's book now, or listening to Sean's book. I'm going to interview him for the podcast in a couple of weeks, and I'm just like fast forward. I mean, I love Sean, and he's a great writer, but I know what the double slit experiment is, and he gave me great advice. When I was writing my book, I'm like, do I have the energy to regurgitate, the Big Bang nucleosynthesis argument, and like he already did it, do I have to? And he told me great advice. He's like, you can tell it the way that you want to tell it. In other words, you can tell it through your eyes. Not that I get to pick my own facts and say, that hydrogen formed, a billion years ago instead of 13 billion years ago. But I get to tell highlight the important aspects through my lens, which was covered by dust, obviously. And I wanted, originally to call my book A Brief History of Dust, but I don't think that would be really, really possible. But what spoke to me is that you're bringing up really advanced subjects, the notion of baryon asymmetry, and readers, I want readers to read the book because these are very advanced topics, but the advanced topics are like the analog to what we want to teach versus what we have to teach. So you mentioned like the inclined plane. So you and I have had to teach the inclined plane. It's part of how we get our salary, right? But on the other hand, we love to teach our brilliant young students who are taking cosmology or particle physics, because that's close to the boundary of what we ourselves are learning about. And there's no better way, or teaching about, there's no better way to learn something than to teach it. And you know that all too well. And what I love about your book is that you don't shy away from things like these really, compared to the price of, sliced bread, it's not that important on a daily basis. But, the baryon asymmetry, the origin of these mysterious things that may indicate very weighty things, the arrow of time, the composition of the universe, the deep, future of the universe. So I wondered if you could not, I hate it when authors are asked, can you summarize your entire book so that nobody has to buy the book? Yeah, I want people to read this book because I think it was a really fast read for me, and it wasn't because I knew everything in it. Quite the contrary. It was very interesting to hear, from a perspective of somebody who isn't a native astrophysicist, as you're saying. But what struck you about astrophysics that caused you to make a pivot, in Silicon Valley speak, into becoming not only a top flight a performer or practitioner of astrophysics, but to really be able to break it down to the public? What drove you in that direction?
So, as a particle physicist, there are really kind of two routes you can take. As a particle theorist, I should say. You can take what we call the top-down road, where you maybe study something like string theory and try to deduce how the universe must work from some sort of grand principle. And usually this involves a lot of mathematics. I mean, all of our work involves a lot of mathematics, but this is even more mathematics. And very rarely does this stuff directly connect with experiments. I learned pretty early in grad school that's not what I wanted to do. That just I like knowing that in 3 years there's going to be an experiment that tells me if this paper I'm writing is right or wrong. And usually it's wrong. Okay, but I like knowing how we're going to get closer to the right answer. And in string theory, it's not obvious that we know that. On the other hand, you can do particle physics from the bottom up, where you say, okay, well, here's a bunch of things we've measured. Some things we don't understand about those measurements are the following. Let's try to work out theories or models or something that can explain those problems and figure out what experiments we will do or should do to find out if that's right. That's much more my kind of MO. That suits my personality quite well. But when I was a grad student, LEP had just finished up. LEP was the electron-positron collider at CERN at the time. They were just finishing. And the Large Hadron Collider wasn't going to turn on for quite a long time. So there wasn't a lot of collider physics that was going to happen in the short interim. So I start thinking about other ways to study particle physics, and in particular ways to study particle physics using the cosmos. So my first project along these lines was talking about how dark matter particles might get captured in the sun, where they would annihilate with each other, they interact and destroy each other, converting themselves into neutrinos. And then we could detect those neutrinos with big telescopes. I was thinking of the ice cube experiments at that time. And I got pretty deep into that. I learned a lot and got excited about it. And then another dark matter project, and then another dark matter project, and then some neutrino astronomy projects, and then some gamma ray telescope projects. And pretty soon I looked around and to my surprise, I'd become an astrophysicist. It was not my plan at all. But given the time and place, it was the right move to do. And now I spend maybe half my time just thinking about the early universe, which is a great thing to be doing right now. With stage 3 and stage 4 CMB experiments, and gravitational waves and all these very exciting things going on, telling us about the first fraction of a second after the Big Bang. I can't help but to be pulled in that direction.
Can you explain to the audience why should it be that these fundamental particles, the smallest things that exist, how they could have any relationship to the entire universe?
Well, I mean, the short answer is the universe is made of elementary particles. And if we specifically are talking about the early universe, as you go backwards in time, the universe was hotter and denser, and the dynamics of hot, dense things are described by elementary particles. So if we go to the core of the sun, we find a bunch of protons and electrons in a plasma undergoing those protons are undergoing nuclear fusion. And I mean, these are laws of physics that following that you wouldn't know about if you hadn't done particle physics kind of experiments. And if you go to even hotter environments, it's not just things like protons and electrons, but things like quarks and gluons, the kind of particles we study at the Large Hadron Collider. In fact, the kind of collisions we study between protons at the Large Hadron Collider tell us a great deal about what the universe was like a trillionth of a second after the Big Bang, when it was full of all the particles that we study at the Large Hadron Collider. And the way we know about the laws of physics that dictated those early moments of our universe's history, we basically know that because we carry out experiments in particle accelerator environments like Large Hadron
Mm-hmm. Right. Yeah. The universe as an accelerator, you brought that up, or you mentioned that. And I think that's something that surprises folks because, it may only be possible to build an accelerator at most on Earth that has the circumference of the Earth. But then after that, you have to start thinking other sorts of designs. But then, as you say, looking back into the early universe, it was essentially a giant particle collider. The fact that these wispy, most minuscule particles, in the case of neutrinos that you mentioned earlier, that they could perhaps have something to do with the structure of the entire cosmos, which is the largest thing we can possibly ever observe. And so I think that is a fascinating thing. I often, a lot of your book talks about dark matter, and it's not surprising for a particle astrophysicist. What, as a human being, just sitting around the bar here thinking about it, I mean, what is your level of disappointment, or are you not disappointed? That say new physics is very difficult to seem to reveal. In that, the discovery of the Higgs was a monumental discovery, but I think physicists expected and promoted and hyped up a lot more possibilities than were actually discovered. And I think so too with the dark matter searches that my colleagues here at UCSD and yours in Chicago and elsewhere are doing, have yet failed to really identify. Are we looking in the wrong place? I often say, to look for your lost keys, you have to look where the light is. But in this case, we should, perhaps we need to pivot the way that we're thinking about, reevaluate the way that we're thinking about dark matter. So just personally, on just a gut level, are you disappointed? Are you hopeful? Are you both? How do you react to the lacuna that we have seemingly to identify in terms of what we previously expected?
Well, yeah, of course I'm disappointed. Like, if you asked me 10 or 15 years ago, I would have given you a very enthusiastic pitch about how dark matter's discovery is inevitable, and I would have been happy to take a bet that we would have discovered the nature of dark matter by now, and I would have lost that bet. In fact, I did make bets like that, and I lost all of them. But
luckily, you work at a very prestigious private school.
Yeah.
For the government.
They weren't high stake bets. Mostly they had to do with honor, even when there was something else at stake.
Okay. Right.
But yeah, I mean, lots of us were really surprised, not just about dark matter, but the lack of new physics being discovered at Large Hadron Collider surprised a lot of us. There were some people who said, more pessimistic things, but most of us in the community were pretty sure that when the Large Hadron Collider was going to discover maybe supersymmetric particles or something else that would address what we call the hierarchy problem or other things, but there was a lot of optimism, even an expectation that by now we would have discovered all sorts of new particle species. When it comes to dark matter, I mean, the arguments we had were based on what kind of particle we thought would have been produced in the Big Bang in the right quantity to make up the dark matter. And we kind of used some arguments, which, okay, they're not bulletproof, but they were suggestive, saying that the kinds of particles that would make up the dark matter would be the sort of particles that we could build these underground detectors and go and look for them, and we should have seen them by now, and yet they're not there. The experiments have been awesome. Like, they performed spectacularly well, but no signals have appeared. So in light of that, we're kind of thinking in different ways. I think you used this analogy before, but instead of looking under the lamppost for our keys, we're getting flashlights out and looking in different places, or finding new ways to look in different places, testing models and theories that maybe we had thought of before, but weren't our high priority back then. But yeah, we're casting a much wider net than we used to. And I guess I'm still cautiously optimistic that this is a problem we can solve. But right now, I'm not as optimistic as about, say, the next 5 years as I would have been if you asked me 10 years ago.
Mm-hmm. That's fair enough. Yeah. Yeah. I mean, I do feel like there is a tendency to kind of overpromise, and we do it in our field too, and as experimentalists, of what we're going to be able to achieve. And it's not, dishonest. It's really what we're, it's our goal. It's what we're striving to accomplish.
We talk ourselves into it, right? We
The confirmation bias, there's the sunk cost fallacy. I mean, the funniest thing is that people think, scientists are, bias free and have no prejudices whatsoever, but a cursory look at, most.
We try.
That we do. Yeah, it's a kind of wishful self-hagiography. But I do think, just getting back into the meat of the book, that really spoke to me was how you really are weaving a story that is, by its nature, it's unfinishable in that we will not have, so you whet the appetite very well, but we, at the culmination of it, I find, left with, there's a sense of wonder and, what we are knowing. I think John Archibald Wheeler said, kind of like science is this island, and you expand the island into this ocean of ignorance. And as you do that, the island gets bigger, but the boundary of ignorance gets bigger too. It just gets bigger a little bit slower. There's a slower power. But I think, the book, and it's a positive thing, but it's disappointing because it really shows, how little we know. And looking back into Weinberg's book 40 years ago now, and again, yours is so comparable to it in many ways. On one hand, it's depressing, but on the other hand, it's kind of exciting to live in a time. Historians look back at Copernicus and Galileo. Oh, well, they didn't even know about, universal gravitation, but they were able to describe things. They weren't discontent with what they knew. They knew there was probably stuff they didn't know, but it wasn't like as relevant, I think, to their daily practice of being a scientist. Now we have all these known unknowns, and really, I think your book highlights these things that we know are true. We know there's a baryon asymmetry. We know that there are neutrinos. We know that there's dark matter. We know that there's dark energy. We know the universe is evolving. But, the why questions, and I think that's a very tough thing to do, and you do it well and give the reader a sense of hope, but also that the scale of the challenge is monumental. And I wonder, as experimentalists, we're kind of singularly focused. We're designing, we're looking at, forecasting, modeling, simulating systematics. As a theorist, on a practical level, what is your day-to-day? What are you doing? What are you thinking about nowadays? I mean, the book obviously takes an enormous, heroic amount of effort. What are you devoting your energy towards now? Is it exploring deeper the topics that are at the edge of time, or is it something completely new and pivoting yet again?
Maybe some of each. I have a personality that likes to take something, really dive deep into it, and then 3 months later be done with it and think about something totally different. So, just today, I had a couple of meetings with my collaborators on a couple of projects. So I'll tell you what today was like.
Yeah.
In one of those, we're talking about a class of dark matter models that could explain this thing called the galactic center gamma ray excess. This was a signal I discovered 10 years ago. And it might be from dark matter particles. We don't know.
Yeah.
And we are, in a very concrete way, working out which models can explain this data along with some other data. It's a very concrete, very bottom-up, very almost pragmatic paper. And then the other one that we're working on, different people, different collaborators, we are imagining what the early universe might have been like if there had been an era where the entire universe was dominated not by matter and radiation, but by black holes.
Mm-hmm.
This is kind of the opposite for me. This is the other extreme. Yeah. This is super speculative, super far afield. But it turns out that it leads to a bunch of kind of cool observational consequences that we can test. Right. And we're working out how these black holes would have evolved, how they would accrete matter, how they would radiate in the way that Stephen Hawking described, what kind of gravitational waves would be produced. We're even considering that they might have produced an observable background of gravitons, which, it's not very often that we get to use graviton in real science. That's almost like such a difficult thing to ever measure. Just for your viewers, a graviton is the hypothetical particle that carries the effects of gravity through space and time, the quantized version of that. And most physicists think that this thing probably exists, but it's virtually impossible to ever measure one. Yeah. So this is pretty far afield stuff. But
he said that about the cosmic neutrino background.
In the book, did I say that?
No, I'm joking. I'm saying they said it was impossible to detect the cosmic.
They did. Okay.
And it still is.
Well, we can see it so that we can detect it in the CMB, right? Well, you know that, of course. But yeah, to detect those particles.
Direct detection, right? Yes.
When I was a grad student, I made a bet with one of the other grad students I went to a summer school with that in 50 years we would detect the neutrinos in the cosmic neutrino background. And I still think that's a good bet.
Can we make a bet? You know, I got some action. I got to get in on this Hooper action.
Offer me one, man.
I got to put my kids through grad school, you know.
You have to make a lot of bets with me to do that. It's not a lot of money.
Especially UC. Well, great. Well, were you done with that particular story, Dan, or do you want to follow up on that? Or
no, that's where I wanted to get.
Okay, great. So I know you're super busy. You've got book tours, and I'm really appreciative of your time. I want to close with a question that I ask all people. We've had artists, poets, science fiction authors. We have a great tradition here at the Arthur C. Clarke Center for Human Imagination in terms of the amount and prolific nature of the artists and authors and scientists that we work with. I always like to ask these visitors on the podcast, guests on the podcast, the same question. I want to ask it to you now, and that has to do with the nature of imagination, of human imagination. And we hear a lot, and you've tangentially thought about this, spoken about this online, at least on Twitter I've seen, but the notion of consciousness, the notion of imagination, the notion of creativity. Are those things that someone like you who's breached many different fields and unified them together in writing, in teaching, and in scientific creativity? Can you teach those things? In your opinion, do you feel, and if so, how do you go about curating, cultivating the next generation of Renaissance men and women, if it's even possible in your opinion? So first, do you think it's possible? And second, if so, how?
So let's break the question into two parts. So I'm quite sure that it is in principle teachable or earnable. I see no reason why it wouldn't be. It's a task like any other, and I'm convinced the human brain is just a very sophisticated and complex machine. If the human brain can do it, then you can teach or build a machine that can do it, and therefore our brains can get better at it. But B, just because I'm confident in principle it can be done, I don't know how to go about doing it effectively. I have not found, like with the grad students I've advised, for example, that I can have a meaningful impact on their personality or kind of way that they approach research. I can teach them scientific facts. I can teach them how to write paper more clear. I can do things like this, but I can't teach them to come up with new and creative ideas. Sometimes it happens. Sometimes they just end up being able to do that. And sometimes they don't. But I haven't personally been able to find any special sauce that enables me to do that. Maybe somebody who knows a lot more about teaching, or psychology for that matter, could, but not me.
Yeah.
If you have any tips, I'll gladly take them.
Well, I always find it ironic that as professors, as basically get thrown in front of a bunch of students, and they never really teach us how to teach. They never teach us about the process of learning. And recently, I started on the process of becoming a flight instructor to supplement the modest income I get here at the state university, at these universities here in California. No, I'm just kidding. I'm compensated fairly. And I find it very interesting and almost ironic that the federal government spends so much more time. Imagine an organization like the IRS, that has a booklet, and huge booklet about the psychology of pedagogy and, the Maslow's hierarchy of needs and all sorts of things. Like I never knew, as my 16 years of being a professor, never once taught. Now, maybe I missed out on it. I know we have resources here. I know you have resources there, but it's certainly not the case that seems to be emphasized, at least in the promotion process, and you're really kind of gauged on your papers, your grad students, your mentorship. on a one-on-one level, but not really on the gross process of as a gross motor skill, so to speak, of pedagogy. So I don't have any secret sauce there, although I am learning a little bit about that, and maybe I can report back once I get my first couple of students that's solo in an airplane, although that might be scary to some people out there thinking about that. Well, I want to be conscious of your time. I really appreciate you joining us here on Into the Impossible, a podcast of the Arthur C. Clarke Center for Human Imagination at UC San Diego. And just give you a chance to do a couple of plugs. The plug zone is open for you. Tell people out on the internet where they can find you and where you're going to be in three-dimensional world in the next couple of weeks, and how to follow you.
Well, you can find Twitter. My handle's Dan Hooper Astro. I'm going to be finishing up this part of my book tour this week. And next week, I think it's on Thursday, I'll be at the Seminary Co-op bookstore in Chicago. And then there's some other things in 2020 scheduled. And I just encourage everybody to check out the book, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. And let me know what you think. I'm easy to find on the internet, so I welcome all constructive criticism or comments.
Great, and yeah, compliments are never to be turned away. Well, Dan, thank you so much, both for your conversation and your wonderful new book. And I definitely encourage folks to look for it. I will leave the links to it and to you in the description for the podcast and the YouTube video. So thank you so much for joining us, Dan. Enjoy the rest of your tour.
Thanks, Brian. I really appreciate it. Thanks for that chance.
The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.